Hello, I'm Amesh Thilavasan, and today I'll be presenting my work on exploring real-world 3D object pose estimation and the Sim2Real gap. In order for robots to learn to perform repetitive, dangerous, and collaborative tasks, such as pick and place in an environment, it first needs to be able to understand what objects are in its environment in the form of their 3D position and orientation. The 3D position and orientation of an object is also known as the 6 degrees of freedom pose, or 6 DOF. One of the major challenges with training deep neural networks for robotic applications is that collecting and annotating real-world 3D object data for pose estimation is both complicated and expensive. Since we cannot manually label real-world 3D data, but do need labeled data for training our models, this work aims at substituting in artificially generated data that can be programmatically annotated and labeled. Once we generate our synthetic 3D data object, we explore how well training on synthetic data generalizes to real-world objects known as the Sim2Real gap. Now I'll cover how I tested a state-of-the-art object pose estimator, deep object pose estimation, or DOPE from NVIDIA, and how well this network can generalize on not just sim-to-sim data, but real-world images. A major motivator for this project was to explore how DOPE generalizes to new and real-world object classes. To test this, we created our own custom object Tetris block to explore generating synthetic data for testing and training, as well as testing real-world sim-to-real transfer. With the CAD model of our custom class, I used NVIDIA's Deep Learning Dataset Synthesizer plugin with Unreal Engine 4 to generate synthetic data and labels by randomizing variables such as lighting, camera perspective, environment, and object pose. DOPE uses multi-stage architecture using VGD19's network pre-trained on ImageNet and then adds several layers to ultimately output belief and affinity maps. Essentially, belief maps are heat maps where the model predict a key point such as a vertex or a centroid, and affinity maps are a vector field associated with each key point. Each vertex or centroid vector is compared to the vector field of that vertex, and then the vector is assigned to the closest centroid. With each vertex of the cuboid assigned, they are passed through a perspective and point algorithm to estimate the 6 DOF of the object by recovering the final translation and rotation of the object with respect to the camera. I performed several experiments. The first was a sim-to-real transfer, and unfortunately, the belief maps for my real-world image were too noisy, so the model could not accurately assign vertices to centroids. To understand why, I created hybrid data by cropping out the synthetic object and merging it with my real-world backgrounds, and the model was able to estimate this more correctly. So this led me to believe that lighting was not generalizing well from sim to real. Moving forward, I performed a series of sim-to-sim analyses testing various synthetic data augmentations, such as applying Gaussian blurs to our data, and the model managed to handle the sim-to-sim well. So to dig deeper into the potential issues, I performed a sensitivity analysis by generating datasets that varied either lighting, camera position, object position, or the environment. Intuitively and quantitatively, lighting showed the largest impact on L2 loss performance by magnitudes over environment and object pose. In conclusion, while this network was able to produce a substantial amount of domain randomized labeled data for the purpose of 6 DOF training and pose estimation, the network still had difficulty spanning the sim-to-real gap, but could generalize well for sim-to-sim data. Next steps are to explore more photorealistic data generation and how to generate labeled real-world data more feasibly. Thank you.